Hello, everyone. My name is Bowen Chang. I'm a postdoctoral fellow at the National Energy Research Scientific Computing Center at Lawrence Berkeley National Lab. Today, I'm going to give a brief introduction and tutorial of our Fair Universe Higgs Machine Learning Uncertainty Challenge. To begin with, the Fair Universe project is a collaboration between the Lawrence Berkeley Lab, University Paris-Saclay, University of Washington, ChalLearn, and UC Irvine. This project is funded by the Department of Energy. Our goal is to build an open, large compute-scale AI ecosystem for sharing datasets, training, fine-tuning large models, and benchmark in high-energy physics. In particular, we are mentioning particle physics and cosmology in this project. Initially, we will host a series of challenges focusing on measuring and minimizing the effects of systematic uncertainty in high-energy physics. The Higgs Machine Learning Uncertainty Challenge is the first challenge of the Fair Universe project. I think most of you have already been familiar with the Higgs boson. Essentially, Higgs is an elementary particle that physicists conjectured 60 years ago in order to provide a mechanism of giving mass to other elementary particles in standard model particle physics. It was first discovered by the CMS and ALES collaboration at Large Hadron Collider in 2012. And later, the theorist who proposed Higgs mechanism won the Nobel Prize in Physics in 2013. So how did people discover Higgs? Actually, we can only discover them in a statistical manner. That is, we didn't observe a single Higgs event. Rather, the way we claim the discovery is to first obtain some expected background distributions and then observe the data to see if there are any significant deviation from the expected background. Through this challenge, we ask a couple of questions. First, can we use machine learning to estimate the signal strength, that is, the ratio between the observed and predicted rates of the Higgs boson decay in the presence of background noises? Second, can we use machine learning to quantify the uncertainty of the signal strength in the presence of systematic biases? To answer these questions, there are a couple of key challenges. First of all, the machine learning model in HEP are typically trained using simulations, meaning that the training data typically include certain assumptions and systematic uncertainty Z. However, the Z value of the real-world data is largely unknown. When applying this trained machine learning model to the real data, the predicted signal strength mu may be biased by the unknown Z. So why do we care about the uncertainty? It turns out that including uncertainties is crucial to the real scientific discovery. By definition, a signal strength of mu equals 1 means that the observed data perfectly matches the expectation. And you can imagine a scenario that your model is trained on some simulation data of Z equals 1, and then you apply your model to a test data with unknown Z. And then your model predicts that there's a signal strength of 1.5. Does it mean that we have discovered something new from the test data? The answer is probably not, because statistical uncertainties and biases from systematic uncertainties may trigger us. Maybe there's an uncertainty of 0.7, which means that it is still likely that we observe something consistent with the original expectation. Therefore, we need a reliable estimator of both the statistical uncertainties and systematic uncertainties. So the common approach to estimating signal strength and its uncertainty is as follows. First, you can imagine that you still train a model on nominal simulation data corresponding to Z equals 1. And then you estimate uncertainties by comparing the results from simulation with different value of Z. You can shift the Z value slightly. You apply your trained model to these different simulation data, and you can observe that the signal strength will vary to some extent. And that will help you get an estimate of the scope of the uncertainty you have. To be more specific, you can, for example, first divide the data into a training set and a so-called holdout sets. Then you can train a simple classifier that attributes scores to each event, where higher scores mean that the event is more likely to be a signal. Lower scores mean that the events are more likely to be a background. So here I show the example histogram of a trained model predictions from a test data. You can see that the Higgs signal here basically have a higher score. If you have a larger signal strength, there's a slightly higher offset in the histogram distribution on the higher score end. While most of the background, for example, from the Z to tau tau, these mostly will have a lower score here because the classifier think it's more likely to be a background. In the step 3, you can then use the holdout sets to independently construct the expected signal and background distributions given different Z values in each bin of the score histograms. This will allow us to quantify the bin likelihood for different nuisance parameters Z. In step 4, basically, you want to do the so-called profile likelihood method to estimate the best fit parameter of signal strength. The likelihood function basically describes how likely the observed data are obtained from a set of parameters. In this case, our parameters are the signal strength mu and nuisance parameters z, although we only care about the signal strength mu in the end. Because we are dealing with the counts in each bin, a natural choice of likelihood is the Poisson likelihood shown in this equation. So you already have the signal distribution from the holdout sets. You already have the background distribution from the holdout sets. Then you can apply your classifier to the test data sets to construct the observed counts in each score bin, which is n over here. Then it is very straightforward to estimate the value of the likelihood. Essentially, we want to estimate mu and nuisance parameters by maximizing this likelihood or minimizing these test statistics over here. As shown in the plots on the right, you can see, for example, suppose the nuisance, there's only one nuisance parameter, then this is basically a two-dimensional fitting problem for the likelihood. You can try to find the minimum of these test statistics, which is over these spots. This means that the best fit signal strength is represented by this blue dashed line, for example, and the best fit nuisance parameter is represented by this red dashed line here. So in summary, mu can be determined by minimizing these test statistics. And because we want to get an estimate of the uncertainty of the signal strength, it is basically this red band over here. The 68.27% confidence level, which corresponds to the 1 sigma range of the uncertainty, will be determined by the value that this relative test statistics equals 1. So let's proceed further. Here is just a quick overview of the datasets of this challenge. Basically, we simulated around 280 million simulated events following proton-proton collisions in Atlas. Each event will have 28 features, which contain 16 primary features and 12 derived features. Each event in the training set also has a ground truth of either the Higgs signal labeled by 1 or background labeled by 0. For the background, there are actually 3 types of background that need to be distinguished from the Higgs signal. The first is the Z boson. The second is the diboson decay. The third is the TT bar background. For more details, you can refer to our white paper and the CODA bench challenge page over here. In this challenge, we parameterize the systematics with nuisance parameters Z. There are 6 systematic uncertainties in this challenge that participants have to take into account. The first category is the feature distorting uncertainties. These 3 nuisance parameters will introduce an overall distortion to some feature distributions. The second category is the background normalization uncertainties. This will introduce overall shift to the weights of specific type of the background events in your dataset. Again, you may want to refer to more details in our white paper and CodaBench challenge website. From the plot on the right, you can see that, for example, if you change different values of the nuisance parameter TES, then some of the feature distribution in the test datasets will be largely shifted and distorted. One useful thing that you may want to know is that on our GitHub repo, we actually provide a series of modules that can be used by the participants. For example, we provide the systematics module that is available on the repo, and that will allow the participants to easily generate new simulation data of different combinations of systematics. So, for example, from this module, you can easily tune the arguments of the systematics here, and that will give you a new dictionary of the data with the applied systematics. When you don't have any value sets for the nuisance parameters here, this function will simply provide you a new data set with 12 derived features that we just mentioned. And you will need those features to train your model. In the evaluation phase, participants' models will be evaluated on 10 sets of pseudo experiments. Each set of pseudo experiments consists of 100 pseudo experiments. And for pseudo experiments here, we are actually meaning test data sets. So there are 100 test data sets in each set of pseudo experiments. For each set of pseudo experiments, these pseudo experiments will share a common true signal strength mu true, but with different nuisance parameter z in order to check if participants' model are robust against different nuisance parameters. Note that both mu true and nuisance parameters are randomly generated. For example, the nuisance parameters are generated through this table. These TES values are drawn from a normal distribution with the mean sigma range shown over here. Only the softmax nuisance parameter are drawn from a log normal distribution with the mean sigma range shown over here. In the end, participants' models need to return the predictions of signal strength for each set of pseudo experiments, and also the 68.27 confidence level for each set of the pseudo experiments. And as you can see here, on a single set of pseudo experiments, there are 100 different test sets. And for 100 different test sets, the nuisance parameters are different, but they share the same true mu here. And your model will basically react differently, have a different estimate of the signal strength and the confidence interval. So that's represented by the blue lines shown over here. In total, participants' model will be evaluated on 10 times 100 equals to 1,000 test data sets in order to win the competition. So to allow participants to easily check their models, we actually provide this ingestion module from our GitHub repo. Participants can easily run the code shown over here. For example, they can use this code to easily evaluate their model with random mu. They can easily use these scripts to impose different systematic over here. And they can run their models on different numbers of pseudo experiments and different number of sets of pseudo experiments in order to check their model performance. With this, participants can save a lot of time to debug their models without really submitting their models to our platform every time. For this challenge, participants will submit their code with trained model to our CodaBench challenge page over here. CodaBench is an open source platform for AI benchmarks and challenges that host our Higgs machine learning challenge. The whole evaluation and scoring process will later be run by the organizers based on participant submissions on an HPC system at NERSC Center at Lawrence Berkeley National Lab. To get started, you simply need to go to our CodaBench page and sign up an account there, then register for the competition. Our CodaBench challenge page and white paper provide all necessary information for the challenge. Participants can easily download all necessary modules and example submissions for some baseline models from our GitHub repo to develop their own models. To make things easier, we have prepared a starting kit with a dummy sample submission file on CodaBench. Participants are encouraged to check the sample submission to get familiar with the requirements in their submission code. We have also created a simplified version of this competition with only one systematics, which is TES, to help participants validate their approaches. Keep in mind that to be considered for a prize, you will need to submit your model to the primary Higgs Machine Learning Uncertainty Challenge. Here is a simple submission workflow for participants on CodaBench. First of all, participants will download the public data from our challenge page. Then they use that data to develop their own models. They can train their models. And in the end, they will prepare a zip file with their model scripts, model.py, and probably also with their pre-trained model. Note that participants are strongly encouraged to submit code with a pre-trained model rather than retraining with the execution to allow evaluation with the research available. So you can then submit your models to the competition websites. Then the organizers will run your model on the back end, and the back end will produce a score based on your model, and that will be updated to the leaderboard if the model is run successfully. And you can keep repeating this whole process until you get a good performance you want. The current deadline of the challenge is March 13, in which the best submission will be taken to phase 2. In phase 2, participants' model will be evaluated on an even larger data set, and in the end, we will get the winner of this challenge to win the prize. If you have any feedback or questions, we are open to that on the challenge workflow and documentation. Please provide your feedback on our Slack channel or even this Google group here. You can also email to these two addresses for collaborations, question, or some general comments. And now I'm going to give you a simple demo about how to submit your solution to our challenge. Simply navigate to the starting kit section of the CodaBench challenge websites. From here, we have a lot of tutorial materials for you. But first of all, let's look at the dummy sample submission. With this, you can easily download some files for an example submission. After downloading the file, you will see a zip file here. If you unzip this file, you will see a script named model.py. Keep in mind that our ingestion program will eventually evaluate your model through implementing this file named model.py. Inside model.py file, you are going to have a class named model as shown here. And then for this class, you can include two arguments, at least these two arguments. The first is to get a train set. The second is the systematics. It is not necessary that you really train your model through this, but just in case that you need to train your model, you can use these two arguments to load a training set after you submit your solution, and then apply the systematics module to the training sets. You also need a function named fits here. And in our evaluation process, the backend will automatically call this function so that your model could be trained after you submit your solution. But it is not necessary that you retrain your model. As mentioned before, there is some computational limits, so we recommend you not to retrain your model after you submit your solution. You will also need a predict function as shown here that has to include an argument named test set. And this test set basically represents the pseudo experiments we mentioned. It will be basically a dictionary containing the test data and weights. And what your model has to return in the end is a dictionary with the following keys. The first is mu hat, which is the predictive value of the signal strength. The second is delta mu hat, which is the uncertainty interval in the predictive value of mu. And you also have to return two values, which represents the bounds of the confidence interval defined by mu hats and delta mu hats here. So for example, you can simply return something like this as a dictionary for the final outputs. So in order to submit this model, simply zip this file to this name, for example, and then we can head to the Coda bench for submission. In the My Submission section, you can simply, for example, name this as a dummy submission, and then just upload the zip file you have. For example, here we're just going to upload this dummy submission, and then your file will be automatically processed. And let's wait over here. Right now, you can see that the status is submitting. And after some time, the organizers will run your jobs. And then when your job is done, basically you will see that the status becomes finished. And you will get a corresponding score like this. You can also see the detailed results of your model performance on different sets of pseudo experiments. Basically, because we just include a simple output that predicts all the signal strengths as one. And also, we didn't include any uncertainty interval. So you can see that the prediction is always a dashed line locating at one, while the true mu here in each different set of pseudo experiment is going to be randomly chosen. Now, let's briefly go through the starting kits to get together. Now, let's briefly go through the starting kits together. From the starting kits, first of all, we will import some of the libraries we need for this challenge. And then we can include some directories that can be linked to the modules that we can use for this challenge. And then we can load the data through the functions provided here. From here, we can further visualize the data feature distribution through the functions we have over here. So users could easily get familiar with how the data looks like through the functions over here. And also we got some of the correlation map here. In the third section of the starting kits, we provide some simple models that the participants can simply try out and try to get familiar with how to perform some statistical analysis that are necessary for this task. And in the end, we also provide some scoring functions and injection function that is going to be performed on Coda bench. With these sessions, we hope the participants can get familiar with what kind of the modules are going to be implemented when their models are evaluated. On our GitHub repo, we also include a few baseline models we provide for the participants to practice. The first one could be the simple one systematic model we provide here. From this file, you can see that there are a few different scripts. The first, again, is the model.py script that is necessary for the submission of your solution. In model.py, we can first, again, have a class of model. And you also, again, you can initialize this with a get trend sets and systematics method here. And also, you need a feeds function as always. Here, there are some reweighting functions that basically allow your analysis to properly account for the number of event counts in each bin in the histogram, and you perform some statistical analysis for the profile likelihood approach. And again, in the end, we need this predict function for the test sets, and that's going to output some of the results we need for the signal strength, which is a dictionary. In this script for the boosted decision tree, it's basically a script that contains the model that the participants want to use. So participants are always allowed to define whatever approach and algorithm they need through different scripts. And in the end, you just need to call these functions in your model.py file. For the statistical analysis.py file, here is basically an independent script that allow the participants to know how to do profile likelihood approach. It is not necessary to do the same thing for your solution, but here we just provide an example about how to fit the parameters to a likelihood, how to build a histogram for signal and background distributions, and also how to compute the signal strength from the output of your classifier. So feel free to look around and feel free to reach out if you have any questions. Thank you very much.